development of applications to guide decisions and to facilitate day-to-day internet operations. He's currently working on the automation and monitoring of entity data's global IP network. Massimo?
So good morning, everybody. We are here with another session of the Internet Measurement Working Group. And it's in English. Outside there are simultaneous translator if you need it. And we can start. We have a really rich agenda. Well, these are the chairs. So the goals of this working group, as always, are the one to bridge researchers and operators. So basically academia, but not only academia, also researchers in the industry with operators, and basically allow them to create this feedback loop that can guide, for example, the future of the internet. This is a collaboration between LACNIC and LACNOG. And this is the agenda of today, and we have the first presentation is our special guest, Jeff Houston. He will present measuring Starlink protocol performance. Then we have Joaquin Feola Pereira that will present traffic engineering at IXP, understanding AS choices. Then we have Vasilis Jostas will present an internet-wide view of large-scale IP sharing on measurement, inference, and service provision. And then Marcus Meyer that will present in the loop an overview of persistent routing loops on the IPv6 and IPv4 internet. So I would say that we can immediately start, and we'll start with our special guest, Jeff Houston, he orchestrated the construction of the first internet network between Australian universities. He is the APNIC chief scientist and an Internet Hall of Fame inductee. And at APNIC, he undertakes research on internet infrastructure, IP technologies, and address distribution policies. I would like also to give him a special thank because he is connected with us at his midnight, so quite late. And then we go straight to the presentation. Jeff, the virtual stage is yours. Thank you very much.
Apologise that I speak Spanish nor Portuguese. The Australian education system very kindly taught me French and German. What can I say? Without further ado, what are we talking about? We're talking actually about tonight, or today, Starlink. It's been not only because Elon Musk has managed to get himself in the headlines for, I think, all the wrong reasons, but it's one of the more fascinating applications of technology in the last few years that have, I think, really revolutionized group Nanog, where they concluded that you had to pick the right TCP to make Starlink really sing and dance. And if you switch from your normal TCP cubic and use DDR, then you got a difference between 1.4 times and 18 times faster when you switch to BBR. Wow, just to change the congestion algorithm gives you a 20 times. Why, when you see Round trip times are up around 2/3 of a second, and the performance is slow and terrible. When you bring the satellite much, much closer to Earth, and by much closer, I actually mean about 550 kilometers up there, really close, then they're going pretty fast. But equally, though, you can make the signals go quick as well. So this low orbit, 500 kilometers, is actually low enough that it's underneath the Van Allen belt. It's protected by the Earth's magnetic shield against solar radiation. So you can actually use quite light, simple electronics at that kind of low Earth orbit and don't need to shield it so much. So at that height, the actual raw signal time to get a signal up and down to something that's 550 kilometers away is just 3.7 milliseconds when it's right above you. And even when it's over near the horizon, 25 degrees elevation, it only takes 7.5 milliseconds to get a signal there and back. So it's quick. Now, it's close to Earth, so even my poor little mobile phone, which, doesn't really have an antenna worth a damn, can actually get and receive a signal, which is fine, but it's not very fast. It really is not very fast. What you actually need to achieve speed is actually a phased array antenna. Starlink call it a dishy, but you need something around 1 meter or so squared in order to get enough signal strength to both send a reasonable signal to the spacecraft and also get a decent signal back. The other issue is that it's so low to the Earth that the amount of Earth that it can beam down to is actually quite limited. It's actually a circle on the Earth's surface at around 900 kilometers of radius. Now, what that means is that you need a large number of satellites so that wherever you are on the Earth, there's always something overhead. The minimum number is about 3,000 to actually do decent coverage, and to get good coverage, you need to go right up there. And that means in launching something like 4,000, 10,000, even in Starlink's case, 30,000 satellites, that's a lot of launch. That's a lot of launch. And traditionally, we used to use disposable rockets. You sent them up, and you just jettison them in the ocean. Really expensive. Starlink pioneered the use of a rocket that landed again, and you've probably seen those images a few times. It's quite a feat. But what it did do was reduce the cost of launch, so that instead of paying around 2,000 to 3,000 US dollars a kilo to get something into low Earth orbit, reusable launch vehicles can get that down to below $700 a kilo and falling. So if you can get that cost down, all of a sudden, these things become economically viable. But there's one more thing about Starlink, which is also really quite interesting. The satellite folk used to run what we call bent pipes. In a bent pipe configuration, you push a signal up to the spacecraft, it's a mirror, it just sends it straight back down to Earth. Now, from a geostationary satellite's perspective, a bent pipe really means that you see half the Earth because you're so far away. So no matter where you are in that hemisphere, you can push a signal up, it'll come back down to Earth somewhere. But when the satellite is really, really close, when you push the signal up, there needs to be an Earth station within about 1,000 kilometers of where you are. Now, that might be fine if you're in, I don't know, where you are now in Sao Paulo. But when you go to somewhere quite remote, and I'm thinking the Simpson Desert in the middle of Australia, or maybe on a boat in the middle of the Atlantic Ocean, there's no Earth station within 900 kilometers of you. Nothing. So what does Starlink do? Well, the way Starlink works is that it actually has satellites in continuous trains. They follow each other in a number of tracks around the Earth. So that when we look at it from a spacecraft's perspective, there's always a satellite dead ahead, and there's a satellite exactly behind you. Now, they're a few thousand kilometers apart, that's fine. But what you actually then do is use a 100 gigabit per second laser link. Yes, space lasers. You don't need optics to guide you. It's space. There's nothing in the way. And those laser links actually set up a 100 gigabit connection between spacecraft, so that when a spacecraft receives a signal and there is no Earth station below, what it does is it beams the signal forward or backwards to the next spacecraft in its train. And it can do so not only one, but multiple hops till it gets to a point where there is a ground Mongolia is that there is no Earth station in Mongolia, politics, and the closest one is in Japan. So the way they do it is they beam the signal up, push it across a couple of satellites, and drop the signal down in Japan. Same way to connect to someone in Mongolia, you go on the terrestrial networks into Japan, beam up and over. Now, when you're low, you're fast. Those satellites are moving at 27,000 kilometers an hour. They go from horizon to horizon in just on 5 minutes. Just 5 minutes. And what that actually means is there's a real tracking problem. So if you look up, and here's a simulation of looking up, I've speeded up time, you actually see that at any point there are somewhere between 30 to 50 visible Starlink satellites at any point on the Earth's surface. And each satellite goes across that visible aperture in about 3 minutes. I could look at that graph, that figure for ages. I think it's captivating. There's just so many satellites up there, even today. So how do we do this tracking? Well, if you actually used a moving dish, it's going to swing really quickly because those satellites are moving very fast. The motors would burn out. And the way we do it instead is by using an old technique called phased array focusing, where it's not just one antenna, but a whole grid of antennas. And by selectively altering the phase of each individual antenna, you can focus where the antenna is actually looking at in the sky without physically moving the dish. The dish is just, flat. And the way they actually do it now is they track each satellite for exactly 15 seconds, which is through 11 degrees of movement, and then move on to the next one. Now, each spacecraft has a relatively large amount of bandwidth. It has 2 gigs of spectrum to work with, and it splits that into 8 channels, each of 250 megahertz. They have 3 downlinks and 1 uplinks. There are 8 beams and 2 polarizations, so 48 beams down, 16 up, which is a relatively hefty amount of bandwidth that it can use. So at any point, in theory, at the signal level, there's 2 gigahertz. The trick is then you use modulation of all kinds of things to extract the maximal amount of bits through that signal. But just be aware of the fact, and it's on the right here, that by tracking a satellite moving across you, what you actually see is a highly varying signal-to-noise ratio. As your satellite moves in front of where you're focused, the signal-to-noise ratio improves, the power gets greater, and you get a clean signal. As it moves away again, the signal degrades. So you get this constantly changing signal-to-noise ratio. Why does that matter? Because the way Starlink actually works is that it is constantly changing its signal modulation to match the available signal-to-noise. That is quite unparalleled in the way we normally set up communication systems. And that's why when you have a Starlink and you start looking at its console, you'll see this constantly changing downlink and uplink throughput reports, which is actually reporting on the signal modulation characteristics, not on the steady state performance of the link. If you look at the steady state performance of a Starlink system, you'll actually see nothing you've ever seen before. On the right is a continuous ping of a Starlink connected device to something on Earth close by the Earth station. This particular one is in California. Every single ping is different from the succeeding ones and the successive ones. what you actually find is a carrier that is astonishingly unstable. And over a long term, and that's the one on the left, you see that the measured performance you can get from these pings correlates to, I don't know, 50 megabits, 100 megabits, one at 900 megabits. And so it's an extremely variable signal, which we've never really used before in communication systems. And the corresponding TCP service has a hard time trying to figure out how fast to go. But it's not just that. It's the scheduling problem. As I said, you get a new satellite every 15 seconds. And each time you switch a satellite, if you look very, very hard at the ping times, you actually see that the minimum latency changes every 15 seconds. And if you look at the same time as packet loss, during these switching changes, it is highly likely you will lose one packet, maybe two, and in the odd times, three, and a massively extended delay time, up to 120 milliseconds just at the time of the switch. Any congestion control algorithm that thinks that loss is congestion, and most of you are running congestion control algorithms that make exactly that assumption, are going to think every 15 seconds you're going too fast. And that's a disaster. Because every single handover has a loss event, or probably has a loss event, and an extended latency. And that's every 15 seconds. So this is the blow up of exactly that same thing across around 30 seconds of timing these continuous pings to show that particular characteristic. So this is not congestion-based loss. You can generally repair it with TCP SAC without needing a session restart. But when the loss gets up a little higher, 3, 4, 5, sometimes TCP gets very, very confused. So the latency should be low. Interestingly, it isn't. The minimum latency we see on most Starlink systems is up around 20 milliseconds. Jitter is extremely high. Why? Well, Starlink uses dynamic channel rate control. It adjusts the modulation of that signal to extract the maximal bit rate across that window of each 1/750th of a second. So in essence, what it's doing is continuously changing the characteristics of the carrier signal to match the available signal to noise. It adds some milliseconds to the round trip times, but also manages to have an extraordinary impact on the amount of bit width you can get from a Starlink circuit. It goes fast, but variable. Now, you say, well, so what? Well, the issue is most of us use TCP across connections. That's the internet. And that uses a thing called ACK pacing. So what it's trying to do is it assumes the circuit is constant, and every time it receives an ACK, it sends another packet. Now, Starlink doesn't provide a dedicated frequency. It doesn't have that stability. It sends 750 frames a second, each frame into 302 intervals, and each frame contains a header that contains the modulation information. So it's a constantly shifting sand. And that becomes what we see as varying capacity, varying delay. And those relative motions, too, of the satellite whizzing overhead generates the problems that we see in transmission. So it's not an easy place to do high-speed TCP, where you've got these regular handovers with loss, dynamic rate control with constant high-frequency jitter, and just to make it worse, damn it, there are other users, and you're doing common channel. So you're doing channel scheduling, so that if I happen to be living next door to a Starlink power user, oh my God, we're sharing so often. And that again means that I've got contention for that channel with other people. So how does all this work? This is a speed test measurement over a couple of years in California. And when I started doing this measurement, it was roughly doing around 100 megabits per second. Over time, as they launched more satellites, it actually got better and the channel contention dropped. And these days it's swinging between 150 and 200, and oddly enough continues to improve over time. So that's Starlink. What about flow control? Well, here are the typical algorithms used by your systems. The red one is Reno, which is an additive increase, multiplicative decrease, that classic sawtooth pattern. There's also cubic, which almost everyone uses, where the increase is actually governed by a polynomial function. And there's BBR. And BBR tends not to queue. It tends to simply oscillate around the onset of queuing. So what happens when I run iPerf3 through Starlink running cubic? What you actually see is the initial slow start, which just stresses out the system until it gets a large amount of packet loss. Cubic collapses down to what it thinks is steady state, which in this case is around 50 megabits per second, and then slowly builds up, finds a loss event, drops up loss event, and so on. But if you actually look, every 15 seconds, I'm going to get a loss event. And sometimes those loss events trigger further collapse in cubic. It's not congestion, but cubic thinks it is. What about BBR? Now, take note of that scale. Same circuit, same system, but this isn't 50 megabits per second. It quickly ramps up to 800 because, BBR. Finds loss to the point where it thinks it's unsustainable, comes back down very rapidly, and then oscillates between 200 to 300 megabits a second. And oddly enough, when I find satellite handover, which gives me a different throughput, BBR almost immediately adjusts and actually manages to stabilize for 15 seconds at whatever is available on the next spacecraft. So that's why BBR does this so well. So if you look at it, Starlink services have these three issues: very high jitter, very high micro loss because of those handovers, and common covariant contention, which is something we all have to live with. Loss-based flow control algorithms work really badly because they actually bring down the available bandwidth. Now, if you're doing content-based constrained connection, voice, even Zoom, video streaming, where the amount of content I'm trying to push through is actually bounded by the content, they actually work quite well. I could be coming over Starlink for this and you probably wouldn't notice it. But if I have to download a few gigabytes or terabytes of data, you're going to notice, because at that point, flow control algorithms will collapse and you need to move to something like BBR to actually get performance back out of the system. Why does BBR work? Because it's not loss sensitive. And that's the big thing about how you actually have to make Starlink work. You need to move away from loss-based congestion control to some form of queuing onset congestion control, which BBR excels at. Other things, use fair queuing. Always use fair queuing. It actually gets you much better performance than bursting. Use selective acknowledgement for TCP because, use it. Not many folk use explicit congestion notification, and I'm not sure Starlink does either at this point in time. But this idea of bringing in the routers to tell you when congestion is happening rather than loss would actually be really helpful for Starlink, because with ECN, commonly going by the name of L4S, you actually find that the congestion window can stay open even when there's loss, which would make things like cubic work a whole lot better. So if you're thinking of using Starlink, no matter what's going on, you'll get decent performance, 40 to 50 megabits per second. Even in Mongolia, 40 to 50 megabits per second, which I think is amazing. In off-peak times when no one else is around and your neighbor isn't a power user, you might get up to 200 to 300 megabits per second. Or if you've sort of tuned the servers and you're using sort of customized delivery, BBR just absolutely flies. Whether it's over QUIC or over TCP makes no difference. BBR will fly. Should I use it for wholesale? Probably not. Not very good for that. But for last mile direct retail access, which is what it's being used for, one-on-one, Starlink just shines. Can we make it faster? Oh God, yes, we can make it faster. Increase the antenna transmitter power, because more power actually means more control over signal quality, and that means denser signal modulation. So increased power means better signal to noise. So that also means higher gain antenna, narrower beams. Drop the orbital altitude from 550 to 340. Give a wider view of the sky and use more bands in the radio spectrum, Ka, V and E band. All of those have been listed by Starlink in October 24 to the FCC in what's happening with Starlink V2 and onwards. That plus 40,000 spacecraft in the sky, which will only be interesting. At the same time, in the current month, Amazon has started launching Project Kuiper. The first launches have gone up, and the Chinese have started launching GoWang. What does this mean? Instead of seeing 30 or 40 satellites in the sky when you look up, it's likely that in a few years you're going to see 2,000 to 3,000, no matter where you are and who you are on the Earth's surface. That's amazing. I just hope they don't crash into each other. I've left a couple of seconds for questions. If there are any questions, I will happily try and answer them. Thank you very much.
Hola. Thank you, Geo, for sharing this great presentation and for joining us at such a late hour for you. Please join me in applause for Geoff.
Thank you.
Do we have any questions in the room or remote for Geoff? Sí.
Yes. I have a device, so I don't know how it is connected to the computer. But if it is an Ethernet connection, there is a signal where you can say stop sending and start sending again. So could this device send a stop sending before each handover and activate sending again after the handover to to have less loss?
There have been various methods to try and customize perform protocols for Starlink behavior. The problem is that Starlink is often in the middle of a long set of connections, and the server at one end in some data center and your computer at the other end doesn't necessarily know that they are connected via Starlink. And even if you did do an Ethernet jamming signal and jammed the sender, which you can do in Ethernet, that jam is not necessarily relayed across to someone who is bridged, or routed remotely inside your house. So you can't do that. The other thing is that Ethernet does not able to jam 715 times a second or as quickly as you get handovers. So no, this doesn't work. The best way to do this is to actually change to a delay-based end-to-end signaling protocol for TCP. That gives you the best performance.
Thanks.
Thank you.
You can also ask questions in Spanish. Yes, please, to the microphone. We have another question.
I'm Rayan Pina. I work for SpaceX Starlink. I think that was a great presentation. I would just like to make a statement, namely that from all the recommendations that the speaker has made regarding improvements to optimize this service, like lowering the satellite height or having more frequency bands, that is not so simple. It's not like going to the supermarket and buying a license. This is a process that takes a long time and requires a lot of legality issues at the level of local governments. For example, if we want to go to Africa, every country is a legal battle. And secondly, Starlink has the purpose of improving and optimizing connectivity in rural areas. Our purpose is not to compete in cities where you have meters of fibers. We're to reach those places where there is nothing at all. Alaska, the deserts. That is what makes us happy. This was just a comment, and thank you for your presentation.
For that, Starlink is notoriously quiet about what it does. And so we researchers try to sort of understand what Starlink is doing by looking and measuring at what we see from Starlink circuits, and also carefully following the filings Starlink make to regulatory bodies such as the FCC in the United States. So yes, I think we agree Starlink works best in rural and remote crowded areas. There's not enough spectrum out there. But overall, let me say, this is an engineering feat that is unparalleled. To do gigabits out of the sky was something that none of us ever dreamt was possible, even a couple of years ago. This is groundbreaking stuff, and not only does it work, but it works brilliantly. So for that, thank you.
We have one more question, Joe. Go on.
Sure.
Good afternoon, everyone. I'm Francisco Lara. I work in .NET from Ecuador. And what we have just had, we are using Starlink connectivity in the Galapagos Islands, 1,000 kilometers away from the continent. So it's very useful there, although there are cities, all the cells are saturated. So my question for Jeff is, from the test you have carried out, is there a packet size or a mesh that is the one that is more efficient, where you have the better performance of the service? Thank you.
The answer with packet sizes, because it uses FEC, forward error correction, and all kinds of signal techniques to minimize bit error rates, do the biggest packet you can get away with. Now, in most cases, this is 1500 octets. This actually gives you better performance than much, much smaller NTU sizes on your circuits. So open the aperture as wide as you can. But more critically, if you've got control of both ends, in other words, you're the server and there are clients out there, the real answer is BBR is the best protocol these days you can possibly run with Starlink. It will give you much better performance than any other TCP protocol. So, like I said, if you have control of both the server and the client, use BBR, really. There's no other way through it.
Thank you very much.
Thank you.
Well, so thank you so much.
Bien, muchísimas gracias, Jeff, por esta presentación. Ahora,
Fiola Pereira. Joaquim is a computer engineer with experience in internet measurements, graduated from the Federal University of Rio Grande. He has worked on projects involving data analysis, performance metrics, and platform development. Currently, he contributes to a project supported by the Internet Society, building tools to enhance the understanding of performance at IXPs. He will be presenting traffic engineering at IXPs, understanding AS choices. Joaquim, please join us.
I would like to thank Elisa for her introduction and LACNIC for the space to address you today. Our work today was done in collaboration with Professor Pedro Marcos. Our purpose today is to provide better understanding on how traffic engineering and IXPs can be understood and understanding AS choices. So traffic delivery is a fundamental aspect of internet operations. This is due to the large traffic volumes that we have. There are different requirements of the applications and also the need for resilience. We also are aware that IXPs are essential elements in this process. This is because they reduce the distances for the participants. This improves the latency as well as a cost reduction when we compare this with the different types of traffic. More and more we have IXPs around the world with greater ASs getting connected, and with this, with ASs with more connectivity, then there are more traffic engineering options, and these are becoming available. So our goal today is to contribute to the understanding of how ASs perform traffic engineering at the IXPs. With this aim, we started analyzing how many ASs are connected to route servers and IXPs. Then, are there any conflicting announcements at the IXPs? And after that, we're going to analyze how, when an AS is connected to multiple IXPs, does it indicate a preference for a specific IXP? And finally, we're going to have a look at whether the AS preference geographically is reasonable at all. So before delving into this analysis, let us speak about the data we are working on. We are working with data from the 3 major IXPs in Brazil, the 3 major IXPs in Europe, and of the data of PIT in Chile. This table summarizes the data that we have available in the route servers. Let me remind you that our analysis also referred to the ASs that are connected to the IXP route service. So when we speak about the prefixes, we are referring to the prefixes that are of the route servers, the prefixes that are announced only by the route server members. These are the overall data, and to collect all this information, this was done through route views, through Looking Glass, and from PCH. All this information was collected on May the 1st. For time constraints, we're going to focus on these 3 types of analysis. I'm going to share with you the results we obtained when they share or don't share the addressing space when they are in the IX. What we noted are different components. In the Brazilian IXPs, we see that there is a larger AS percentage that shares their entire space, the addressing space. For European IXPs, we see that there's a reduction. Only half of the ASs that are connected to the European IXPs announce all the addressing space.
Announce all their space, and the same we see for Chile. As to the analysis that we consider that is more valid to approach, there are issues of a conflicted announcement in IX, and we have 2 different scenarios. The first is when a member of IX announces something and another member of the route server announces the same prefix. That may happen in 2 different ways: by announcing the same prefix exactly, or announcing a more specific prefix by another member. Here we're going to illustrate starting with the same prefix. We have the red AS, the blue one. Both are connected to the IXP's route server. The 2 have an external connection to IXP. The red AS propagates route /L24 and the other one to the blue AS. As a consequence, the blue one connected to the route server will go through that route again. The way we design it, the traffic would go as expected. When the route server, that the blue one that wants to connect it with the red one, would do it directly. Now here there's a different scenario. One of the member announces the two same prefixes, but when they put it into the route server, he uses the prepend, is sort of blowing its route. So the traffic would flow unexpectedly. And why do we say that? Because the ASs in the route server that want to communicate with the red AS communicate first with the blue one, and then, only then, will they communicate with the red one, something that doesn't make sense, considering that the red one is in the route server and has direct access as well. So there are more specific cases of more specific prefixes, and we illustrate it in the same way. We have the red AS and the blue one, both connected to the route server, the two of them with an external connection to the route server. However, here the red AS will announce a /23, and the blue one has a more specific announcement. When the blue AS announces this more specific prefix of the route server of the IXP, we know it that they will choose the most exact, so it would flow unexpectedly. How would this work? Let's see the scenario, but does it really happen in real life? Here we see a table showing the total number of members in each IXP. We do not consider announcement intersections between AS siblings because they belong to the same organizations. So now let's see whether these cases do occur. I highlighted that indeed many of the members in Sao Paulo, for instance 90%, present some intersection in there is another announcement coinciding with some other member. In the case of the unexpected traffic flow, does it happen or not? What we see is that despite the fact that many members have an intersection, we have fewer cases when the traffic flows unexpectedly, but we need to pay attention there, because it might not make sense for me to talk with X if then I'm going to talk with Y if I can talk directly to Y. So the second scenario that we illustrate has to do with this situation when an AS is a member of the route server and does not announce part of its addressing, but there's another member that announces that prefix, and the same owner of the resource did not announce. Let's illustrate that. So here you have the red AS, the blue AS, the same connections in the route server, external connections to the IXP, and the red has a /23. Part of the /23 will announce in the route server, and the other part will be announcing to the blue AS. When the blue AS puts this in the route server, we know that this can lead to a traffic flow reaching the red AS because it has to hop where it was unexpected, because that was not announced. So the traffic gets there, but unexpectedly. Let's see whether this indeed happens in the IXPs that we are analyzing. We have the total number of members of IXPs and SPs, and this does happen. It does happen. There are many members that even as they have their routes and their announced prefixes, and they do not announce them themselves, and as a result, traffic may flow and unexpectedly reach a point where the AS is not expecting it to come in. And when the ASs are in multiple IXPs, does that indicate a preference for one or the other? Here we have a chart with a line for each pair of IXPs. We have the number of members, and finally the last column is intersection of the members. So here, for instance, if we consider Sao Paulo Fortaleza, we have 356 ASs with common IXPs. To avoid any biases in our data, we're going to work only with the cases where we have 100 ASs in common in the two IXPs. How do we classify whether the AS is indicating a preference or not. We base on 3 key techniques: selective, more specific announcements, and the use of prepending. For each AS that is connected in 2 IXPs, we are going to focus on one of these 4 metrics. No pref indicates that the AS announces the exact same prefixes at both IXPs with no distinctions. We say pref A when the AS is connected with 2 IXPs but indicates a certain preference, for instance, to exchange traffic with the IXP A. And the same with pref B, but in this case the preferred one is IXP B. We have the case, for instance, of the mixed. Let's say that for some prefixes, when the AS is in 2 IXPs and indicates a certain preference for part of its prefixes, may prefer IXP A, and for the other part, it prefers IXP B. Let's see how it gets classified in our chart. So, we have the metrics represented here. We have the colors for the metrics that we mentioned. On top of the chart, we have the number of networks. And what do we see? What is striking here? Among the Brazilian IXPs, almost half of the ASs do exactly the same announcements. This is showing that they do not indicate preference for exchanging traffic with none of the 2 IXPs. In the case of the European, when the ASs are connected to M6 and links, they prefer the 6 or links. If it's very difficult, they prefer the 6. Now, when the European ASs, when the ASs are connected to different European links, then in that case, the DC, DE6 and links, but they make the announcements exactly the same. The preference of the ASs. Does it make sense if we geo-localize the prefixes? Well, starting with a case study in Sao Paulo, Fortaleza, let us talk about the prefixes where there's no preference. On top of the map, you see the IXP of Fortaleza, and down there, the one of Sao Paulo. Each green dot indicates the ASs connected in the IXPs that do not indicate preference. We have a cluster close to Fortaleza and another cluster in Sao Paulo. What we think is that considering the geographic distance between the 2 IXPs, shouldn't we determine some type of a preference? Don't you have such a thing in the terms of to avoid latencies? In the second case, we speak of the same IXPs, but now with the prefixes where there are preferences. Here we painted in red, there that indicates the preference in São Paulo, and in blue when they prefer to exchange in Fortaleza. What was striking was that most ASs prefer to exchange traffic in the IXP of Sao Paulo. However, 13% are closer to Fortaleza. And so we wonder whether that preference is correct. So, in a nutshell, what we just saw, according to the region and the IXP, the ASs are going to more or less say their addressing time. There are conflictive methods that require our attention because they may make traffic flow unexpectedly, or that they may reach somewhere where they were not expected. We also have ASs connected to multiple IXPs that tended to make the same announcements, exactly the same. Now, when they don't do it, the tendency is for them to prefer one over the other, and many prefixes. Beyond the fact that many prefixes are geolocalized close to Fortaleza, the preference is to exchange traffic with Sao Paulo, and that can result in higher costs in latency. And with that, I finish my presentation, and I'll stay here available for questions.
For questions, again, you can ask in English, Spanish, Portuguese.
Hola, Edmundo Cázares de IAR México.
Casares from Mexico. Edmundo Casares. I have a doubt. The clusters that you identified that have preference to exchange in Sao Paulo and those that prefer to exchange in Fortaleza, did you draw any metrics? I don't know, but the average latency that leads to one preferring one or the other. One of the things that we did was we measured it according to the geographic distance, but we didn't see the penalty. So I believe that it would be at least 20 milliseconds considering the speed of light, but in kilometers and the milliseconds that have to be added.
Thank you very much for your presentation, and another round of applause. And we go to the next presenter. The next presenter is Vasilis. Hey, he's already here. So he will present internet-wide view of large-scale IP sharing on measurement interface and service provision. Vasilis is a senior research engineer at Cloudflare, working in network measurement, telemetry, and security of critical internet infrastructure. He was an assistant professor at Lancaster University, where he led the network security research. He has played a key role in multiple mission-critical research projects funded by the UK National Cybersecurity Center and the US Department of Homeland Security. Vasilis, the stage is yours.
De Seguridad Nacional. Muchísimas gracias. Hola a todos. Este es un trabajo de colaboración con un grupo, Nirgut y Antoine Cordelet y Nick Wood y Stefan Rubin y Marwan Fayed. Hoy vamos a analizar cómo compartir la IP a gran escala, pero primero vamos a explicar por qué querríamos hacerlo.
IP-based filtering is one of the most popular security techniques, and it can be done either with block lists, where we drop completely traffic from IPs that we have found to be participating in past attacks, or by rate limiting the number of requests an IP can send. Or sometimes something a bit more sophisticated is by trying to detect anomalous patterns of requests, right? Deviations from what someone may consider a normal IP behavior. One problem with this widespread technique is that it may incur collateral damage. And what I mean by that is that every client has an IP, but an IP can have multiple clients behind it, sometimes hundreds or even thousands. And I particularly talk about two types of shared IPs. Carrier-grade NATs, which are used by ISPs in order to accommodate multiple users behind the same IP, so they preserve the scarce IPv4 address space. And VPNs or proxies, which essentially are options by the user who wants increased privacy or sometimes performance. So one key distinction between carrier-grade NAT IPs and VPN and proxies is that CGNAT is not a choice of the user, right? They may not even know they're using CGNAT Actually, I'm pretty sure most users have no idea what is CGNAT, which means that if one of the users behind a CGNAT gateway misbehaves, it would be unfair to punish every user behind the same gateway, right? So this is something that is very undesirable. On the other hand, we've observed purposefully malicious abuse of VPN IPs over time. Unfortunately, if you do a quick Google search, you will see that a lot of CGNAT users are frustrated often because they are being blocked or they are being throttled and have no idea why that happens. And in the past, the UK regulator for communications, Ofcom, did a report on the implications of CGNAT. And one of the things they pointed out is that, indeed, this is a problem for CGNAT users. They are being blocked, although they have done nothing, right? And users sometimes blame ISPs because they use CGNAT. Other times blame the security providers, like Cloudflare or Google. So we need to do something about it. What's even worse, if that was not already bad enough, is that there is a socioeconomic bias on which users are being affected. In this map, we see the number of available IPs per user, and you see that developing countries in particular have much fewer IPs per user, so they have to rely even more on CGNAT, meaning that these security techniques affect developing economies more. So the goal of the work we're doing is that we are trying to detect which IPs belong to CGNATs and VPNs and which IPs are not shared, so that we calibrate IP filtering, and we try like that to minimize the implications of this filtering to users of shared IPs. How we try to do that? The main idea is quite simple. Since we're a large CDN, we observe billions of HTTP requests from billions of IPs per day. So we try to extract some features from these HTTP requests per IP and build what we call a supervised machine learning classifier, right? So we have some training data, we feed it the features, we create a model, and then we use this model to predict the type of IPs we observe sending requests. And like that, we can distinguish CGNAT IPs from VPNs or from non-large-scale shared IPs. This is pretty standard in machine learning, right? That's very basic. What is important here is what features we select so that they are informative enough to distinguish these different types of IPs. And importantly, how do we find a training data set that will be labeled with a type of IPs, right? How do we know which IPs are CGNAT or VPN or nothing of these types so that we train this classifier? Unfortunately, there is no readily available data set on CGNAT IPs in particular. There are some lists with VPNs, nothing, though, definitive on CGNATs and non-CGNAT IPs. So we try to employ a combination of techniques to measure those things. First, we run distributed trace routes from RIPE Atlas. And in the trace route path, we try to detect whether there are private IPs or IPs in the shared address space before going to public address space. So in this trace route, you hear the highlighted hops. We go from private address space to shared address space and then to public IPs, which is a strong indication that CGNAT is deployed in this case. Another way of collecting CGNAT IPs for our training data set is by parsing whois records, parsing the description field, which sometimes indicates the use of the IP. You can see here, it's explicitly mentioning that this resource is used for CGNAT. And other times, there are hints encoded in the pointer DNS records of IPs. So we do an internet-wide DNS scan. We collect those PTR records, and we try to parse the strings to extract those hints. Like that, we constructed a relatively extensive data set of, let's say, ground truth IPs. We have hundreds of thousands of IPs in many thousands of ASs all over the world. Now, I acknowledge that all of these sources of information on their own are imperfect. The actual technique is much more nuanced, but I have to skip some of the details. We are going to publish a more detailed report on exactly how we construct it, and I'm happy to discuss with you later. But having collected these IPs, the next question is, how do we select the features that would be informative? So we go to our HTTP logs, and we try to find features that would signal a large user population behind an IP. And these features can be volume of requests, but also diversity of clients. For instance, diversity of user agents per IP, which encode operating system, browser, device type, and so on. It can be diversity of TLS fingerprints per IP. An important feature we have found to be RTT variability, because users behind CGNATs and VPNs are spread across larger geographical areas. And we aggregate those features for the duration of a day, and we feed them to our classifier. So we use a simple classifier, XGBoost, which performs well for imbalanced data. And it actually performs very well. We found it to be 98% accurate, 97% F1 score. The important bit here is that we can distinguish well VPNs from CGNATs, because as I said earlier, it's very undesirable to block CGNAT IPs, but for VPNs, it's sometimes desirable. And what helped us to do that is that we aggregate the features I mentioned before, not just per IP, but also per /24 prefix. In these distributions here, you see the distribution of, let's say, distinct user agents in plot A per IP, in plot B per covering /24 prefix. Blue line is non-cert IPs, non-multi-user IPs. Red is CGNAT IPs. Green and yellow are VPNs and proxies. And you will see that when we look at the per IP distribution in plot A, the blue line stands out from the rest. So per IP distributions can help us distinguish non-cert IPs from cert IPs. Now, if we go to plot B and we see the distribution of user agents per /24, suddenly the CGNAT IPs in red are apart from the VPN and proxy IPs. And if you think about it, it makes sense, because usually CGNATs are allocated block of IPs, while VPNs and proxies may have separate IPs in separate prefixes. Now, that's why when we plot the feature importance, the /24 aggregation of the features is the more informative. So we applied this technique on the Cloudflare data, and we tried to analyze the blocking and throttling done by our clients. What we found is that, first, CGNAT IPs generate about 16 times more requests compared to the non-cert IPs. And that may make them appear suspicious to someone. And indeed, when we see how often those IPs are throttled, like those CAPTCHA things you often get, they are throttled 3 times more often than non-cert IPs, although they have the same bot score. The bot score is a score that we assign to each IP based on whether we believe it's a bot or not. And despite they don't have different bot score, they are blocked much more often, right? And we see that the global distribution is indeed skewed. The highest raw numbers are in the US, Brazil, and India. But if we see the proportion of IPs, then you can see on the lower map that many countries in Africa stand out, and Southeast Asia, right? So indeed, to have equitable security measures, we need to take this IP sharing into account. So to conclude, it seems that it is possible to identify these shared IPs in the wild. It is important to do that in order to minimize collateral damage. Diversity of characteristics, and not just volume, is a key, as well as the aggregation per IP and per /24 prefix. I want to draw your attention to a recent IETF draft proposal on prefix lengths. This proposal defines some RPSL tags that would allow ISPs to self-publish which of their IPs are CGNAT, and then like that it will allow us, like security providers and content providers, to treat those IPs more lightly, right? Not block them, not throttle them as much, and so on. And finally, I want to ask you, if you are an ISP and if you use CGNAT, to share this information privately, of course, with us, so that we can improve our training, we can improve our filtering, and I think this is both for the benefit of our users and also the benefit of ISP users. Thank you very much. I am ready to take questions if you have any. Thank you.
Thank you, Vasilis.
Thanks.
Do we have any questions for Vasilis? No? I'll ask you a question then. There may be CGNAT IPs with a small number of subscribers. How can you infer those?
Sí, hay despliegue de CGNAT que no tienen muchos suscriptores. Creo que lo que resulta importante es detectar los CGNATs que tienen muchos suscriptores, porque estos son los que se ven afectados por el tipo de filtrado equivocado y por el bloqueo equivocado. Y de esa manera lo llamamos de gran escala. Bueno, muchas gracias.
Marcus Meyer.
Nuestro próximo presentador.
His current research focuses on network security and the underlying infrastructure of modern networks. He conducts large-scale measurements to investigate anomalies, such as his current work on routing loops. He will be presenting In the Loop, an overview of persistent routing loops on the IPv6 and IPv4 Internet.
Thanks for the introduction. Hi, I'm Marcus, and I'm going to bring you a short overview of persistent routing loops and the IPv6 and IPv4 Internet. So, first of all, why routing loops? So, during some unrelated large-scale Internet measurements by our colleague Florian, we found a large number of time-to-live exceeded error messages. So, usually time-to-live exceeded error messages are a result of the packet we sent off had a too low time-to-live value, and the path was too long for that packet to reach its destination. However, during those measurements, we actually scanned using the maximum value of 255. So we should reach every target on the Internet. So that is actually a strong indicator for routing loops. So first, what is a routing loop? Let's take a look at this small topology. We are the sender and want to send a packet towards the prefix to 001, DB8, 100 to 1. So we send the packet to our default gateway, which in this case is router A. Router A has a specific route towards the prefix of size /48 and forwards it appropriately towards router B. However, router B only has a more specific route of /64 for another prefix that is not that does not contain our target IP. Thus, it also sends it back towards its default gateway, and router A and router B play ping pong with the packet until it gets dropped. So this is a small working example of a routing loop. Two other terminology I need to introduce. Again, take a look at this small infrastructure here. We again a sender, and we are gonna send a packet towards network S. However, there is again a routing loop between router B and router C, so the packet never reaches network S. That means network S is shadowed by the loop, thus we are calling them a shadowed network. We cannot reach network S as all packets get trapped within the loop. On the top of the topology, we have network I. Network I is fully reachable. We can ping targets in there with no problem. However, it is endangered by the loop as it has at least one router that is part of the loop on its path. So if anyone would attack the loop, performance might degrade, or even worse, the link goes down, thus endangering the entire prefix. So therefore, we call it imperial networks. Let's go to how we designed the measurement. First, we are taking the BGP data from CADA, which is based on route views, but enhanced with AS data. For every /24 prefix in IPv4, we take one random IP address and do a full trace route to it. We do the same for a random IP address in every /48 prefix. After doing the full trace route to all those destinations, for each route we are doing a full loop detection to check if towards that destination a loop is found. So next, we have all these loop candidates, but these are only loop candidates, and these loops might be because of some dynamics in routing protocols, BGP, and so on. So we need to check whether they exist for long times. So for each loop we take up to 10 destinations and recheck them a month later to see if they are still existing or not. We are also doing that from two different vantage points to check whether this is a local phenomenon or a global one. Finally, we are checking each prefix that is shadowed by scanning 50 IP addresses in each prefix to see if we only hit an unlucky IP address or if the entire prefix is shadowed. That results in about 3 terabytes of raw data after the 26 days of continuous packet sending. So let's go to the results here. First of, I'm gonna compare our study to the study of 2005. This was the study in 2005 was the last study done before ours, so there was a large gap of knowledge. They traced around 5.5 million targets in IPv4. We more than doubled that to 12 million. And in IPv6, we traced around 5.5 billion IP prefixes. So for IPv4, of those 12 million targets, we found 35,000 routing loop candidates. Of those, only around 23,000 routing loops stayed persistent after the month. For IPv6, around 161,000 routing loop candidates we found. Of those, 30,000 stayed persistent after the month. So where does that leave it at shadowed and imperial prefixes? So you can see with only 23,000 loops, around 109,000 prefixes in IPv4 cannot be reached. And 860,000 prefixes might be endangered due to routing loops because they have at least one router on its path from our vantage point. In IPv6, this is even way dramatic. We found around 121 million prefixes that were not reachable from our destination because they had a routing loop on its path. And a staggering 1.2 billion prefixes, so a quarter of the entire target space, was imperial as it had at least one router that is part of a loop on its path. So let's go into detail on how those loops look. First, I'm going to take a look at the loop length. So with loop length, I mean how many routers are part of such a routing loop. First detail you can see is most of the loops are of length 2. For IPv4, we have around 82% of all loops, and in IPv6, we got around 91% of all loops. So the majority of routers play ping pong with only 2 routers. The next interesting thing is we found a lot of loops with loop length 1. That doesn't make a lot of sense, because that would mean one router is sending the packet back to itself. In IPv4 around 15%, and in IPv6 around 6% of all loops were of this length. We are not quite sure why this is happening. We found some papers that were talking about middle boxes that were hiding the traffic behind them that might result in such things. The other reason that might be is MPLS that hide the real IP address of such loops. Other than that, around 3% of all loops were of length 3 or higher. So you can see the most loops are here are really short. Continuing, persistence of location. Our main vantage point was in Vienna, so here we have all our loops found. We also did the persistence scans in Sydney and Virginia. Around 80 to 82% of our loops also were observable in Sydney. In Virginia, around 87 to 88% of our loops were seen. If we take a look at all the loops that are seen from all 3 vantage points, around 75 to 77% can be seen globally. So you can see this is not a local phenomenon only happening in Austria. This is a global phenomenon. So lastly, let's take a look at persistence over prefix. So is the entire prefix we traced only with a single IP address to, is it shadowed, or is the IP address unlucky? So IPv4 here in green, you can see we have a large bar at 0 and at 50. That means either 0 or 50 answers to the prefix where time to live exceeded. So that means either only the single IP address is shadowed or the entire prefix, most likely. In IPv6, this is a bit more distributed and across the entire range, but we have the most of time to live exceeded messages here at 50, so that's a stronger indicator towards the entire prefix being shadowed. Last, AS attribution, so who is responsible for that? We looked into how many AS are usually part of such loops. As you can see, around 92% of all loops, only a single AS is responsible for a loop. We also took a look at if the preceding router, so the router in front of the loop on its path, is also in the same AS, or if it's in a different one, that is rather split in the middle with 50 to 42%. 8% of our loops had 2 ASs, and only below 0.5%, 3 or more ASs were part of a loop. That brings us to the last detail here. How dangerous are loops for uninvolved ASs? So the table here, in each row, you can see the AS that controls the shadowed network, if it is also involved or not involved in the loop. And in column-wise, you can see if the AS that operates an imperial network, so that that's endangered by a loop, is also part of the loop or not. So the interesting column here is imperial and other AS. That means that 14.43% of loops do imperial AS, prefixes of AS, that are not involved in any loop. So those are the hard ones to fix. In the other percent, most of the time, only the own AS are imperial, so endangered. For IP4, this looks rather similar. Here, 16% of prefixes owned by ASs that are not part of a loop. So that brings us to my key takeaways. You might want to take a look at that. So most of the loops are of length 2. So as these are all manual misconfiguration errors, this most likely means that we have here a high number of missing pull-up or black hole routes. So if you have IPv6 deployed on your CPE, please check if you have those pull-up routes. Further, 76 or 84% of the loops shadow only their own AS. So those loops are low risk because the responsibility is only at their own AS. So they can fix their own issues here. However, 16% or 14% of the loops imperial uninvolved AS, those, as I said, are the important ones because they cannot fix the issue themselves. They have to talk to other ASs, which might be a bit harder than everything else. So with that, thanks for your attention, and I'm open for questions.
Thank you very much. Thank you very much, Marcus, for this presentation. Questions, again, Spanish, English, or Portuguese, of course. Okay, then I have one for you. So, you did this analysis, but do you have any data related to routing loops per region?
Yes, I would have, and I would also have a backup slide, but my slides are gone.
The slides, please. Can you put back the slides?
So, to begin speaking, we see, as we are based in the RIPE region, most of our targets. Okay. Yeah. Can I go quickly? So, there we go. This is the data per rear split up. As you can see, or not, the first bar is target addresses, and the fourth one is persistent routing loops. There you can see in blue RIPE NCC. So half of our targets at the time were at RIPE NCC. The bar above it is LACNIC in that case. So you can see LACNIC only has around 15% of the entire target space. However, what is interesting here to see is, I'm very loud suddenly, okay. Persistent routing loops are at least double the size. So even though the target space for LACNIC was rather small, there were a lot of routing loops found during the time. So that indicates a lot of misconfigurations here. Other regions were moderate here. So thanks for the question.
Thank you very much again. Thank you. And
thanks.
Pleasure. We can close this session, this edition of the Internet Measurement Working Group. The slides. And, okay. Okay, we do without the slides then. Oh, we have it. We have it? We have it. No, yes. Okay, perfect. Okay, let's go to the... just some closing remarks. The first one is we have a mailing list that you can see here. This mailing list is really useful if you do experiments, if you are a researcher, also if you are an operator and you want to provide feedback. It's used to exchange ideas. It's also used to exchange, I don't know, questionnaires or to show your research. There is also a mailing list for the chairs if you want to provide feedback on comments on presentation. And of course, remember to get ready. We are going to have another opening for presentation in October in El Salvador. And there will be in the mailing list, of course, the call for presentation. I would like to thank again all the speakers, my amazing co-chair Elisa, and the stenographers that they help us with the translation. And of course, thank you for being here. Thank you very much, and see you in October. Bye-bye.